Have you ever looked up at the night sky and wondered what secrets the planets might be hiding? Picture Venus, often called Earth's twin, cloaked in thick clouds of sulfuric acid, with surface temperatures hot enough to melt lead. For decades, we've seen it as the ultimate hostile world, a place where nothing could possibly survive. But what if there's more to this shimmering, mysterious planet than meets the eye? What if, hidden within those swirling, golden clouds, lies a phenomenon so strange, so unexpected, that it could completely change our understanding of not just Venus, but of atmospheres everywhere? This is the Venus mirror effect, one of the most tantalizing and little understood mysteries in modern planetary science. Imagine, for a moment, a natural mirror suspended high in Venus's atmosphere, reflecting energy in ways that defy our current models, creating what some researchers believe could act like hidden portals or windows into other layers of reality. It sounds like something out of science fiction, but cutting-edge observations and theoretical studies are suggesting that this might be very real. Scientists are only just beginning to unravel how such an effect could work and what it might mean for our search for life, for energy, and for deeper truths about the universe. This isn't just about one planet, it's about rewriting the rules. It challenges everything we thought we knew about atmospheric dynamics, light behavior, and even the nature of dimensions themselves. In this video, we're going to embark on a journey to explore this incredible possibility. We'll dive into the science, the mystery, and the mind-bending implications of the Venus mirror effect. You'll come away not just with new knowledge, but with a sense of awe at how much remains unknown, waiting right next door in our cosmic neighborhood. So let's begin. So what exactly is this mirror effect that scientists are observing? To understand it, we first need to picture the atmosphere of Venus itself. It's not a single, uniform blanket of gas, but a complex system of layers, each with its own unique properties. The most prominent feature is that thick, global blanket of clouds made mostly of sulfuric acid droplets, which sits about 30 to 40 miles above the scorching surface. For a long time, we thought these clouds behaved in predictable ways, absorbing and scattering sunlight. But recent data from probes and telescopes has revealed something astonishing. In specific regions of the upper atmosphere, energy, particularly in the form of infrared and microwave radiation, is behaving in a way that defies all expectations. Instead of being absorbed or scattered randomly, it's being reflected back with a startling coherence, almost as if it's hitting a perfectly smooth, glass-like surface. This is the heart of the Venus mirror effect. It's the detection of these bizarre, anomalously strong reflections that act like a natural mirror hanging in the sky. They create intense, localized bright spots in the data that scientists simply cannot explain using our current models of atmospheric physics. It's as if there's an invisible boundary layer up there, one that's far more structured and reflective than any known cloud type could possibly be. This phenomenon doesn't just slightly deviate from predictions, it completely contradicts them, suggesting there's a fundamental process at work that we have not yet discovered. Now, the idea of a mirror naturally leads to thoughts of reflection and duplication, which is where the more speculative and fascinating implications come into play. The effect is so precise that some theorists propose it could, under certain conditions, create an optical illusion of a duplicate world. It's not that there's a literal second Venus, but that the mirroring could potentially project a coherent image of one part of the atmosphere onto another, or even trap and recirculate energy in a closed loop. This creates the concept of a hidden portal, not a science fiction Stargate, but a natural atmospheric window or a lens that bends the rules of energy and perception. It challenges our most basic assumptions about how light and energy interact with matter in extreme environments, suggesting that the atmospheres of planets might be capable of far more complex and mysterious phenomena than we ever dreamed. But the story of this mystery doesn't begin with our modern, powerful telescopes. Its roots stretch back to the first robotic pioneers we sent to brave the planet's hellish environment. In the 1970s and 80s, a fleet of spacecraft from NASA and the Soviet Union began to peel back the layers of Venus's secrets, and they immediately started sending back data that didn't quite add up. The Pioneer Venus orbiter, launched in 1978, was equipped with a sophisticated radar system designed to map the planet's surface through its impenetrable cloud cover. While it succeeded in creating our first global topographical maps, the data was peppered with strange, persistent glitches. In certain areas, particularly over the highland regions known as Alpha and Beta Regio, the radar would return signals that were anomalously bright. It was as if the radar waves were hitting something far more reflective than the expected volcanic rock, a signal so strong it was initially dismissed as an instrument error. Around the same time, the Soviet Venera missions, which included orbiters and hardy landers that briefly survived the crushing pressure and immense heat on the surface, were making their own bizarre observations. The Venera orbiters, studying the atmosphere from above, detected unexpected and sharp variations in the density and composition of the upper cloud layers. Their instruments picked up fleeting but intense reflections of light, brief flashes that seemed to originate from within the cloud deck itself, not from the surface below. The landers, during their daring descents through the acidic haze, transmitted data showing sudden, unexplained temperature inversions and pockets of atmosphere that were curiously clear of droplets, as if they were falling through a temporary void in the cloud. For the scientists analyzing this data back on Earth, these were more than just minor curiosities. They were persistent anomalies that survived repeated verification. Each time a new mission confirmed the same strange readings, the whispers grew louder. The initial assumption was always a flaw in the instrument or an error in data processing, but the patterns kept appearing. The unexplained radar bright spots were consistently in the same locations. The optical flashes were observed by multiple different spacecraft. This wasn't random noise, it was a signal. It was the first hard evidence that there was a phenomenon occurring in the atmosphere of Venus that lay completely outside our understanding of physics and chemistry at the time. These early probes didn't have the resolution or the specific instrument suites to solve the mystery, but they provided the crucial, tantalizing clues that something extraordinary was waiting to be discovered, setting the stage for the deeper investigations to come. These early anomalies were puzzling, but it's the precision of modern observations that has truly cornered scientists with a paradox that seems to break the known laws of physics. To grasp why this mirror effect is so deeply baffling, you have to understand what should be happening in that atmosphere. Venus's skies are a chaotic soup of supercritical carbon dioxide, sulfuric acid droplets, and other volatile compounds. This isn't a calm, stable environment. It's a raging, turbulent mess where gases and aerosols are constantly mixing, colliding, and absorbing energy. In such a dense and complex medium, light waves, especially those at infrared and microwave wavelengths, should be absorbed by the gases or scattered in all directions by the countless droplets. Think of shining a flashlight into thick, churning fog. The beam doesn't reflect back at you in a clean, sharp line. It gets diffused, softened, and ultimately lost. That is exactly what every atmospheric model predicted for Venus. Yet, that is not what we see. Instruments like the Venus Express Orbiter's VERITAS spectrometer and ground-based radio telescopes have detected something that simply shouldn't exist: incredibly sharp, coherent reflections. These aren't faint glimmers, they are intense, localized bursts of energy bouncing back as if they've hit a pane of glass. The most confounding aspect is the specific wavelength at which this is happening. The reflections are strongest in a narrow band of the near-infrared spectrum, a wavelength that carbon dioxide and sulfuric acid are famously efficient at absorbing. It's the equivalent of finding a spot in the middle of a scorching desert that is somehow covered in a perfect, unmelted sheet of ice. The very elements that should be gobbling up this energy are instead, somehow, reflecting it with near-perfect efficiency. This creates a fundamental physics problem. Our conventional models of light-matter interaction, which work perfectly well for explaining rainbows on Earth or the haze on Titan, completely fail here. They cannot account for a mechanism that would create such a specular, mirror-like reflection in a gaseous medium. A true mirror requires an extremely smooth surface on a microscopic level, like the polished silver behind glass. A random cloud of acid droplets is the exact opposite of that. It's the definition of rough and uneven. For these droplets to align in such a way to create a collective mirror effect would require a level of order and stability that the violent, swirling Venusian atmosphere isn't supposed to possess. Scientists have run simulation after simulation, tweaking variables for temperature, pressure, and composition, and nothing in their digital toolkit can recreate this phenomenon. It suggests there is either a previously unknown state of matter forming in those clouds or a fundamental gap in our understanding of how light behaves under extreme conditions. This isn't just an oddity on a distant planet, it's a direct challenge to the textbooks, forcing physicists to question if they've been missing a piece of the puzzle all along. To truly appreciate the strangeness of this mirror effect, we need to take a virtual journey up through the atmosphere of Venus, layer by treacherous layer. Starting at the surface, it's a crushing, infernal landscape. The pressure is 92 times that of Earth, equivalent to being nearly a kilometer underwater, and the temperature is a constant 870 degrees Fahrenheit, hot enough to turn lead into a puddle. This hellish foundation is blanketed by a thick, hazy fog of carbon dioxide and other gases for about 20 kilometers up. But as we ascend further, we enter the planet's most defining feature, its main cloud deck. This cloud deck is immense, stretching from roughly 48 to 68 kilometers above the surface. It's within this vast, swirling golden shroud that we find our mysterious zone of interest, a specific band between approximately 50 and 70 kilometers up. This is the arena where the mirror effect is being observed, a region that should be, by all accounts, the most chaotic and disordered part of the entire atmosphere. The clouds here are primarily composed of sulfuric acid droplets, constantly condensing and evaporating in a violent cycle. Winds scream at hurricane force, whipping around the planet in a phenomenon called superrotation, completing a full circuit every 4 Earth days while the planet below barely rotates at all. Now let's focus on the specific conditions at an altitude of around 60 kilometers, right in the sweet spot for these bizarre reflections. The temperature here is surprisingly almost Earth-like. It hovers around 86 degrees Fahrenheit, and the pressure is nearly the same as we experience at sea level on our own planet. For a fleeting moment, you might think this is a place where humans could potentially exist. But the devil is in the details, or rather, in the deadly composition. The air is still unbreathable carbon dioxide, and it's saturated with those corrosive sulfuric acid droplets. This combination of habitable temperature and pressure with a lethal chemical makeup is the first great paradox of this zone. This brings us to the core of the scientific conundrum. This specific altitude range possesses all the ingredients that should make a stable, mirror-like reflection utterly impossible. Think of it like trying to create a perfectly smooth pane of glass inside an industrial blender. The winds are ferociously turbulent, creating constant shear and mixing that should tear any organized structure apart. The cloud particles themselves are not uniform. They exist in a wide range of sizes and are constantly in flux, colliding, merging, and breaking apart. A mirror requires a smooth, stable surface on a microscopic scale. What we have here is the definition of disorder and chaos. Furthermore, the chemistry is all wrong. Sulfuric acid is highly absorbent, particularly of the specific infrared wavelengths that are being reflected back with such startling clarity. It's this perfect storm of volatile conditions, the turbulence, the ever-changing particle sizes, and the absorbent nature of the medium that makes the detection of a coherent reflection so revolutionary. We are seeing a phenomenon of exquisite precision emerging from what should be pure bedlam, and that is what forces scientists to reconsider what might be possible within the hidden dynamics of planetary atmospheres. Now, this brings us to the most daring and controversial interpretation of all. If our conventional physics can't explain the mirror, could it be that we're seeing something far more exotic, a natural portal or gateway woven into the very fabric of the atmosphere itself? This idea, often labeled as science fiction, is actually being discussed in serious, albeit speculative, theoretical circles. The core of the proposal rests on the unique and extreme conditions found in that specific layer of Venus's atmosphere. The combination of immense pressure, corrosive chemistry, and wild temperature gradients creates an environment of such intense energy that some physicists believe it could be capable of warping the local structure of spacetime in fleeting ways. The theory suggests that within this atmospheric soup, quantum fluctuations, tiny, random pops of energy and matter that happen everywhere all the time, could be amplified to a macroscopic scale. On Earth, these fluctuations are so small and short-lived we never notice them. But in the ultra-dense, hyper-energetic environment of Venus's upper cloud decks, they might, for an instant, become stable enough to create a temporary wrinkle or fold in reality. Think of it like a tiny, natural particle accelerator operating on a planetary scale, potentially generating conditions similar to those we try to create in massive underground colliders. These folds could act as wormhole-like structures or dimensional windows, not for spaceships to travel through, but for energy and information to be reflected or transmitted in ways that appear to us as a perfect, inexplicable mirror. Proponents of this view argue that Venus acts as a colossal natural laboratory, demonstrating physics that we simply don't have the means to replicate or observe anywhere else. The mirror effect in this context wouldn't be a reflection off a physical surface, but a glimpse of energy momentarily taking a shortcut through a higher dimension or a different state of being before re-emerging into our own. It's a mind-bending concept that pushes the boundaries of known science, suggesting that our sister planet isn't just a hostile world, but a key to understanding the deeper, hidden workings of the universe, a place where the veil between dimensions might be at its thinnest. Of course, the most grounded approach is to first look for answers within the bounds of our established science, and researchers have proposed several compelling natural phenomena that could be mimicking this bizarre mirror effect. The leading candidate involves the very stuff those clouds are made of, sulfuric acid. We know these droplets exist in a wide range of sizes, and some scientists theorize that under the unique temperature and pressure conditions at that 60-kilometer altitude, these droplets might undergo a process called coagulation, merging into much larger, more uniform particles. If a vast layer of these similarly sized droplets were to form and remain stable for a time, they could, in theory, act like a collective surface, reflecting light in a more coherent way than a disorganized mist ever could. It's akin to the difference between the choppy, scattered reflections on a windy lake versus the near-perfect mirror image you see on a perfectly still pond. Another fascinating possibility involves exotic metallic compounds suspended within the acid clouds. Venus's volcanic activity is believed to be constantly pumping various elements into the atmosphere, including metals like iron, lead, and bismuth. At those scorching temperatures, these metals can vaporize and rise into the cooler upper clouds, where they might condense onto the sulfuric acid droplets or even form their own unique crystalline structures. Certain metallic compounds are incredibly reflective, especially in specific infrared wavelengths. A fine, glittering mist of metallic frost floating within the cloud deck could potentially create the intense, localized bright spots that our instruments are detecting, acting like billions of tiny, natural mirrors. There's also the potential for previously unknown atmospheric chemistry to be at play. The violent mixing of sulfur dioxide, water vapor, and other gases under intense ultraviolet radiation from the sun could be creating novel types of aerosols, exotic chemical compounds we haven't yet identified or studied in a lab. These unknown particles might have optical properties that defy our current expectations, perhaps absorbing energy at one wavelength and re-emitting it at another in a way that looks to our remote sensors just like a sharp reflection. Yet, for all their ingenuity, each of these conventional explanations hits a formidable wall when held up against the full body of evidence. The sulfuric acid droplet theory struggles mightily with the issue of stability. How could a layer of uniform droplets form and, more importantly, maintain its structure for long enough to create such a precise reflection in the midst of hurricane-force winds that are constantly tearing everything apart? The metallic compound idea is compelling, but we have yet to detect the concentrations of these metals in the upper atmosphere that would be required to produce such a dominant reflective effect. Our spectral analyzers just don't show a strong enough signature for them, and while unknown chemistry is always a possibility, it remains a scientific placeholder, an acknowledgement of our ignorance rather than a testable solution. The most critical problem they all share is that they still don't fully account for the sheer intensity and coherence of the reflection, particularly at that specific wavelength that carbon dioxide should be absorbing. These natural theories brush up against the mystery, but they haven't yet managed to embrace it fully, leaving a compelling gap in our understanding that invites even more profound questions. This journey into the quantum realm might seem like a leap, but it's a necessary one to grapple with the sheer strangeness of the data. The core problem, as we've seen, is that a chaotic gas shouldn't act like a polished mirror. To explain this, we have to venture beyond the comfortable rules of classical physics and into the probabilistic, often counterintuitive, world of quantum mechanics. Here, the behavior of particles is governed by waves and probabilities, not billiard ball collisions, and it's in this domain that some researchers are finding tantalizing, albeit speculative, answers. The most promising avenue involves a concept known as a Bose-Einstein condensate. In everyday matter, atoms are a jumbled mess, all vibrating and bouncing around at different energies. But under specific conditions of extreme cold and very low density, atoms can lose their individual identities and collapse into a single, unified quantum state. They essentially act as one giant superatom, a coherent wave of matter. This isn't just a laboratory curiosity. It's a fundamental state of matter with unique properties, including something called superfluorescence, where the entire condensate can absorb and then re-emit light in a perfectly synchronized, coherent burst. Now consider the environment in that specific layer of Venus's atmosphere. While it's not ultra-cold, it exists at a pressure and temperature that is, for certain compounds, a sweet spot between a gas and a liquid. Some theorists propose that the complex soup of sulfuric acid and trace metals, under the immense pressure and with a constant influx of solar energy, could be forced into a macroscale quantum state unlike anything we've ever seen. Instead of a disorganized cloud, you might have a vast, thin film of matter behaving as a single entity. This coherent sheet could then interact with light in a unified way, reflecting specific wavelengths with the perfect efficiency of a mirror, not because of a smooth surface, but because of a unified quantum state. This idea naturally leads to an even more profound possibility: macroscopic quantum entanglement. Entanglement is the bizarre phenomenon where two particles become linked, so that affecting one instantly affects the other, regardless of the distance between them. We've proven this works for pairs of particles, but what if it could scale up? What if the unique, energy-saturated environment of Venus's upper atmosphere is acting as a natural crucible, entangling not just pairs of particles but vast clouds of them? If billions upon billions of aerosol droplets were to become entangled, their properties would be inextricably linked. This could create a network of communication and coordination that would force the entire cloud layer to behave in a synchronized, non-local way. A photon of light wouldn't just hit one droplet, it would effectively interact with the entire entangled system at once, and the system would respond as one. The reflection we detect from Earth wouldn't be a simple bounce, it would be a coordinated quantum response from a continent-sized swath of atmosphere. This would explain the impossible coherence and intensity of the mirror effect, suggesting we're not looking at a weather pattern, but at a single, massive quantum object hanging in the sky of another world. Of course, these are extraordinary claims, and they remain firmly in the realm of theoretical physics. No one has ever observed quantum coherence or entanglement on such a monumental planetary scale. The environment of Venus is brutally hostile to the delicate conditions usually required for these states, yet that is precisely what makes this mystery so compelling. It forces us to ask if our understanding of quantum mechanics is incomplete. Perhaps we've only observed these effects in the quiet, controlled isolation of our labs, and we've missed how they might manifest in the riotous, energy-dense cauldron of a real planetary atmosphere. The Venus mirror effect, therefore, is more than just a puzzle about one planet. It's a potential window into a new frontier of physics, one where quantum weirdness isn't confined to the microscopic realm but can rise up to shape the very skies of a world. So where do we stand today in our quest to solve this atmospheric riddle? The baton has been passed from those early, rugged pioneers to a new generation of orbiters armed with sensors of astonishing sensitivity. The European Space Agency's Venus Express mission, which circled the planet from 2006 until 2014, provided the first great leap forward in data, and what it found only deepened the mystery. Its VERITAS instrument, a sophisticated spectrometer designed to map the surface and atmosphere in infrared light, didn't just confirm the strange reflections, it revealed their stunning complexity. The data showed that these weren't random glitches, they were structured, recurring features appearing most prominently over the massive highland regions like Aphrodite Terra. The infrared signatures indicated areas where the atmosphere was behaving less like a chaotic gas and more like a layered, reflective surface, with specific polarization patterns that suggested an incredibly ordered arrangement of particles, something utterly foreign to our understanding of cloud physics. Even more baffling were the temperature readings. In these same zones of anomalous reflection, Venus Express detected sharp, localized cold spots in the upper cloud decks. This is a huge clue because temperature and reflectivity are intimately linked in atmospheric science. A colder region often indicates a different composition or a change in density, but these cold spots were coupled with the brightest reflections, creating a paradox. It's as if the most efficient mirrors were also the most effective at cooling themselves, a combination that points toward a physical process that is both radiative and highly organized, something far beyond simple cloud condensation. The anticipation now turns to the future, to two missions that promise to be game changers. NASA VERITAS orbiter, set to launch within the next few years, will peer through the clouds with a powerful new radar system so precise it could map the entire surface of Venus with higher resolution than we have for most of Earth's ocean floor. But beyond topography, its other instruments are tuned specifically to hunt for the source of these atmospheric anomalies. It will measure gravitational fields to understand the planet's internal structure, searching for a link between subterranean geologic activity, like massive volcanoes, and the strange energy being channeled into the skies above. The theory is that heat and gases venting from powerful volcanoes could be providing the raw material and energy needed to fuel these exotic atmospheric processes, creating temporary, stable conditions where none should exist. Then there's DaVinci, perhaps the most daring mission of all. It won't just orbit, it will plunge directly into the mystery. The DaVinci probe is designed as a descending sphere that will brave the acidic hell, sampling the atmosphere all the way from the upper clouds down to the surface. As it falls through that critical 60-kilometer altitude zone, its suite of instruments will act like a medical biopsy, taking the atmosphere's vital signs with unprecedented detail. It will measure the chemical composition of every gas and droplet it encounters, directly sniffing for those speculated metallic compounds and exotic aerosols. It will count the size and shape of every particle, searching for evidence of the large, uniform droplets or crystalline structures that could explain the mirror effect. Most crucially, it will be looking for those fleeting, microscopic clues, tiny variations in noble gas isotopes or unexpected chemical bonds that could hint at quantum-level phenomena or previously unknown states of matter occurring right there in the air around it. This isn't remote sensing anymore. This is going into the heart of the storm to finally touch the mystery itself. While our modern orbiters provide stunning detail, some of the most tantalizing clues about this mystery were actually gathered decades ago, locked away in the archives of the Soviet space program. The Russian Venera missions were marvels of engineering for their time, designed to survive a descent into what was essentially an acid bath under crushing pressure. We've all seen the grainy images of the rocky surface from the landers, but that's just a fraction of the data they collected. During their harrowing plunges through the cloud layers, these probes were constantly transmitting a stream of information from their sensors readings that, for various reasons, were never fully analyzed or publicly released in their entirety. In recent years, planetary scientists and historians have begun sifting through this treasure trove of old data, digitizing analog tapes and re-examining the findings with modern analytical tools. What they're discovering is startling. Beyond the well-known surface images, the descent modules of Venera's 11, 12, 13, and 14 recorded bizarre anomalies in the specific altitude range where the mirror effect is now observed. Their nephelometers, instruments designed to measure cloud density, reported sudden, drastic drops in particle concentration. In one case, a probe's sensors indicated it had fallen through a vast, unexpected void in the clouds, a literal tunnel of clear air surrounded by the acidic haze. This wasn't a momentary blip, it was a sustained anomaly lasting several minutes of the descent. Even more intriguing are the rumors surrounding the optical sensors. The official releases focused on the panoramas from the surface, but the probes also had instruments taking readings during the descent. Whispers among researchers suggest that some of these sensors captured fleeting, intense flashes of light reflected from within the cloud deck itself, far brighter than anything the sun should have produced under those conditions. These weren't lightning strikes, they were coherent, directed beams that saturated the instruments. At the time, these data points were likely written off as instrument error or electrical noise caused by the brutal descent. But today, viewed through the lens of the mirror effect hypothesis, they look less like glitches and more like early, raw detections of the very phenomenon we're now struggling to understand. This reanalysis suggests the effect isn't a rare event, but a persistent, widespread feature of the Venusian atmosphere, one that the pioneering Venera probes stumbled through on their way to the inferno below. This idea of a quantum haze or a suspended film of coherent matter is strange enough, but it leads us to an even more profound and dizzying possibility. What if the mirror we're seeing isn't just bending light, but bending time itself? This is the core of the time mirror hypothesis, a theory so radical it sounds like it was pulled from the pages of a science fiction novel. Yet it's a concept some physicists are seriously considering to explain the most baffling aspect of the data. Remember those anomalous radar bright spots first detected by the Pioneer orbiter over places like Alpha Reggio? Modern missions like Magellan, which mapped Venus in exquisite detail in the 1990s, went back to look at those same spots. What they found was utterly perplexing. The incredibly bright, mirror-like reflections were indeed coming from specific geological features, but there was a disconnect. The intensity of the reflection didn't always match the current topography of the area. It was as if the radar was seeing a ghost image, an echo of a landscape that was no longer there. In some cases, the reflection patterns suggested surface features that were smoother, younger, and less cratered than the terrain we see today. It's the equivalent of pointing a radar at a weathered, ancient mountain and getting a return signal that indicates a pristine, gentle hill. This is where the temporal reflection idea gains traction. The theory proposes that under the immense pressure, peculiar chemical composition, and violent energy fluxes of the upper atmosphere, the very fabric of space-time could become locally warped. We know from Einstein's general relativity that massive objects like stars and planets warp space-time, creating gravity. But on a much smaller, more localized scale, extreme atmospheric conditions could, in theory, create minute, temporary wrinkles in this fabric. These wrinkles might act not as portals to other places, but as windows to other times. They could briefly connect the present moment with the past, allowing light, or in this case, radar waves, to travel down, hit the surface from a bygone era, and then travel back up through this temporal shortcut to be detected by our instruments in the present. Think of it like an optical echo. If you've ever shouted into a deep canyon and heard your voice come back to you a moment later, you've experienced a delay as the sound waves travel. A temporal reflection would be a similar echo but for light, and the delay wouldn't be a matter of seconds but of millions of years. The energy from our radar pulse would be traveling into the past, reflecting off a younger version of Venus's surface and returning to our present. This would perfectly explain why we see reflections of terrain that appears younger. We might be catching glimpses of Venus as it was in its more geologically active youth, before volcanic plains hardened and meteorite impacts scarred its face. The mirror in the sky wouldn't be made of acid or metal, but of distorted time itself, offering us a fleeting, incredible view into the planet's own ancient history. But with such an exotic phenomenon potentially at play, we're immediately confronted with an enormous, towering question. What on Earth, or rather, what on Venus, could possibly be powering it? To sustain a planetary scale effect that seemingly defies the laws of entropy, you would need a truly colossal and constant source of energy. We're not talking about a simple weather pattern here. We're discussing something that appears to impose a bizarre order onto one of the most chaotic atmospheres in the solar system, and that requires a staggering amount of power. So where could this energy possibly be coming from? The most obvious suspect is the Sun itself. Venus is closer to our star than Earth is, bathing in nearly twice the solar radiation. This immense influx of energy is the primary driver of the planet's hellish greenhouse effect and its super-rotating atmosphere. One theory suggests that this solar wind, a constant stream of charged particles from the Sun, could be interacting with Venus's upper atmosphere in unique ways. Unlike Earth, Venus lacks a global magnetic field to deflect this onslaught. Instead, the solar wind slams directly into the planet's ionosphere, the upper layer of its atmosphere that's been ionized by solar radiation. This collision creates a dramatic and dynamic process where the energy from the solar wind is transferred to the atmospheric particles, potentially exciting them to higher energy states. Some researchers speculate that this constant, violent interaction could be funneling energy down into the lower cloud decks, providing the power needed to sustain large-scale quantum coherence or to form those speculative metallic compounds. It's like a natural, continuous particle accelerator operating right in the sky, charging the atmosphere with the raw power needed for these strange effects. Another compelling source lies deep within the planet itself. Venus is thought to be a world of intense, widespread volcanism. While we lack definitive proof of current eruptions, the planet's surface is young, geologically speaking, covered in vast lava plains and thousands of volcanoes. If Venus is indeed volcanically active today, these eruptions would be pumping enormous amounts of thermal energy and volcanic gases directly into the atmosphere. This isn't just about heat, it's about chemistry. Volcanoes could be belching out vast plumes of sulfur dioxide, water vapor, and those critical trace metals like iron chloride and bismuth sulfide. This constant injection of fresh material could provide the precise chemical ingredients needed to form the reflective layers, while the raw thermal energy from the molten rock below could power the atmospheric convection that organizes it. The mysterious mirror effect is often observed over major highland regions like Aphrodite Terra, which are thought to be hotbeds of tectonic activity, creating a tantalizing potential link between the planet's internal furnace and the mysteries in its sky. Yet, for all their promise, both of these conventional explanations run into serious, perhaps insurmountable, problems when we break down the actual energy requirements. The sheer scale and precision of the reflections suggest a phenomenon that is not just powerful, but incredibly efficient and stable. The solar-wind interaction, while energetic, is notoriously chaotic and uneven. How could such a turbulent, unpredictable source of power generate the conditions for a stable, coherent quantum state or a perfectly smooth reflective layer? It would be like trying to power a precision laser with a lightning storm. The energy is there, but it's the wrong kind. It's disordered and destructive, not ordered and constructive. The internal heat theory faces a different but equally tough challenge rooted in Venus's bizarre rotational dynamics. Venus rotates on its axis incredibly slowly, taking 243 Earth days to complete a single turn, and it does so backwards compared to most other planets. This sluggish spin means the planet has an extremely weak Coriolis force, the effect that on Earth helps organize weather systems into rotating storms and jet streams. Without this organizing influence, the transfer of heat from the interior to the atmosphere should be messy and inefficient, creating general chaos rather than localized, structured phenomena. How could internal energy rising through this disorganized atmosphere be focused so precisely to power a specific, stable effect at a very specific altitude? It's as if all the energy from a volcano was channeled not into a massive plume of ash, but into forming a single, perfect, floating crystal pane of glass miles above the crater. The physics of how that could happen remains a complete mystery, pointing toward the possibility that we might be missing a fundamental piece of the energy puzzle altogether. This forces us to consider the most radical possibility of all, an unknown energy source or a completely novel form of energy transfer. Could the Venus mirror effect be its own source of power? Some theoretical models explore the idea of a self-sustaining atmospheric circuit. In this scenario, the initial energy from the sun or volcano's kick starts the formation of a coherent, reflective layer. Once established, this layer itself begins to drastically alter the local energy dynamics. By reflecting specific wavelengths of infrared radiation back down toward the planet instead of letting them escape into space, it could trap energy in a closed loop, creating a positive feedback system that continually reinforces its own structure. The mirror would, in effect, be powering its own existence. Other, more speculative ideas delve into the realm of zero-point energy or quantum vacuum fluctuations. The idea that empty space itself is not truly empty but seething with transient particles and energy. Under the extreme conditions on Venus, this background sea of energy might be being tapped into or amplified. It's a concept that pushes the very boundaries of theoretical physics, suggesting that the planet's atmosphere might be acting as a natural resonator for the universe's fundamental energy field. While this remains firmly in the realm of hypothesis, it underscores a critical point. The persistent failure of conventional energy models to account for the mirror effect isn't just a small gap in our knowledge. It's a glaring signpost pointing toward potentially revolutionary physics, waiting to be discovered in the swirling, golden clouds of our neighboring world. This bizarre mirror effect high in the Venusian atmosphere might seem like a distant curiosity, a scientific puzzle confined to our sister planet. But what if the forces at work there hold a startling, urgent relevance for us here on Earth? The key to this connection lies in a simple, powerful concept: energy balance. Every planet is in a constant, delicate dance with the energy it receives from the sun and the energy it radiates back out into space. This equilibrium determines its climate and its fate. Venus presents us with a dramatic, extreme case study of this balance gone awry, a runaway greenhouse effect that turned a world potentially like our own into a scorching hellscape. The mirror effect adds a bizarre new twist to this story, and by studying it, we might be peering into a distorted mirror of our own future. The core of the climate connection is albedo, which is just a scientific term for how reflective a surface is. Think of a fresh snowfall. Its bright white surface has a high albedo, reflecting most sunlight back into space and helping to keep things cool. A dark asphalt parking lot, on the other hand, has a low albedo. It absorbs that solar energy, heats up, and radiates warmth back into the air. Earth's climate is profoundly sensitive to changes in albedo. The rapid melting of polar ice caps is a prime example. As brilliant white ice disappears, it's replaced by darker ocean water that absorbs more heat, which in turn melts more ice, creating a vicious warming cycle. This is a feedback loop we understand all too well. Now consider Venus. Its thick cloud deck has a very high albedo, which is why the planet shines so brightly in our night sky. For decades, we assumed those clouds were our planet's saving grace, reflecting enough sunlight to prevent an even more extreme greenhouse effect. But the mirror effect complicates this picture enormously. It suggests that the reflectivity of Venus's atmosphere isn't a uniform, predictable blanket. Instead, it might be dynamic, patchy, and capable of forming intensely reflective, localized zones that behave in ways our climate models never anticipated. If such unpredictable, self-reinforcing reflective patterns can emerge naturally in a complex atmosphere, it forces us to ask a troubling question. Could similar, albeit less extreme, phenomena be occurring in our own skies? This is where the research gets truly fascinating for terrestrial climatologists. They are beginning to explore how unusual aerosol layers and chemical interactions in Earth's upper atmosphere might be creating their own subtle, unexpected reflective effects. For instance, the persistent contrails left by high-altitude aircraft can sometimes spread out to form thin, wispy cirrus clouds that trap heat, but under certain conditions they might also enhance reflectivity. More profoundly, massive volcanic eruptions inject huge quantities of sulfur dioxide gas high into the stratosphere, where it transforms into tiny sulfate aerosol droplets. These droplets are brilliant reflectors of sunlight, and a major eruption can actually cause a measurable, temporary global cooling, as Mount Pinatubo did in 1991. This is a human-observable, large-scale version of a reflective atmospheric phenomenon. The Venus mirror effect takes this concept to a theoretical extreme. It shows us that under the right, or rather, the terribly wrong conditions, an atmosphere can develop reflective layers of such efficiency and stability that they fundamentally reorganize how energy flows across the entire planet. On Venus, this might be trapping heat in some regions while creating bizarre cold spots in others, driving atmospheric circulation patterns we can barely comprehend. For Earth scientists, this is a cautionary tale written in the clouds of another world. It demonstrates that our atmosphere is not a simple, passive system. It is a dynamic, chaotic, and potentially unstable entity, capable of developing its own unexpected and powerful responses to the immense amounts of energy we're pumping into it through greenhouse gas emissions. Understanding the physics behind Venus's mirror could provide us with a new set of rules, a new language for describing how reflective particles can organize and behave. This knowledge could be the key to interpreting subtle, hard-to-examine changes happening right above our heads. It might help us predict whether certain types of pollution could inadvertently create more persistent reflective layers, or whether warming-induced changes in cloud composition could alter Earth's albedo in dramatic ways we haven't forecast. The hellish world next door, with its mysterious shining mirror in the sky, serves as a grand natural laboratory. By deciphering its secrets, we aren't just solving a planetary puzzle. We might be gaining the foresight to navigate the complex and uncertain future of our own planet's climate, learning to read the warnings written in the reflections of another world. Of course, the presence of such a profound and seemingly technological mystery in our cosmic backyard was bound to ignite the most imaginative explanations. When conventional science grapples with the unexplained, it creates a vacuum, and into that vacuum flow theories of ancient alien civilizations and advanced technology. The Venus mirror effect, with its suggestion of a perfectly engineered reflective surface, is a prime candidate for such speculation. Proponents of these ideas point to the sheer precision of the phenomenon. They argue that a natural cloud, no matter how unique, could never achieve such a coherent mirror-like quality. The reflections are too sharp, too organized, too intentional. For them, this isn't a weird weather pattern. It's the glint of sunlight off a colossal manufactured structure, a solar shield, an energy collector, or perhaps even the roof of a vast floating city designed to inhabit the only remotely hospitable zone Venus has to offer. The appeal of this theory is undeniable. It transforms a distant scientific puzzle into a tangible, thrilling narrative. It suggests we are not just studying a planet, but potentially the artifacts of an intelligence that mastered its environment in ways we can scarcely conceive. These theorists often draw parallels to other purported anomalies in our solar system, weaving a tapestry of cosmic archaeology where Venus is just one chapter in a much larger story. The idea that a civilization could have evolved to live permanently in the clouds, having given up on the infernal surface below, is a compelling science fiction concept that resonates deeply with our own anxieties and dreams about humanity's future among the stars. However, the skeptical perspective offers a powerful and grounding counterargument, rooted in the brutal reality of Venus itself. The surface conditions are not just hostile, they are outright apocalyptic. With temperatures that melt lead and pressures that crush submarines, the notion of finding permanent, solid structures built on the ground is virtually impossible. Any material we know of would be quickly degraded and destroyed by the relentless heat, pressure, and corrosive chemistry. If an ancient civilization did exist on Venus, the planet itself has almost certainly erased all evidence of it from the surface. The geological turnover from likely ongoing volcanism would have buried any ruins under miles of lava, making the idea of finding a Venusian geyser a geological non-starter. This effectively pushes all extraterrestrial speculation up into the clouds, to that narrow, temperate band where the mirror effect occurs. But here, too, skeptics find overwhelming obstacles. While the temperature and pressure are Earth-like, the atmosphere is still a suffocating cocktail of carbon dioxide and sulfuric acid rain. Building and maintaining any large-scale structure in this environment would be a monumental engineering challenge, far beyond anything we can currently envision. The super hurricane force winds that scream around the planet would subject any physical object to unimaginable stresses, tearing apart anything not perfectly designed to withstand constant, violent turbulence. Furthermore, if such a structure existed and was actively reflecting energy, our most sensitive instruments should be able to pinpoint its exact location, shape, and composition. Instead, what we see is a phenomenon that appears and disappears, shifts locations, and behaves more like a dynamic atmospheric process than a solid, static object. The most compelling middle ground in this debate may lie in a more nuanced interpretation. Perhaps we are not looking at a constructed object, but at a manipulated process. Could the mirror effect be the signature of technology that is not still operational, but whose remnants are still influencing the environment, Imagine a scenario where an ancient civilization, facing their planet's descent into a greenhouse catastrophe, attempted a desperate, last-ditch geoengineering project. They might have seeded the upper atmosphere with trillions of self-replicating nanomachines or exotic reflective particles designed to cool the planet by increasing its albedo. This project could have initially worked, only to eventually fail as the machines malfunctioned or the planetary conditions worsened beyond repair. What we observe today might not be a working machine, but its ghost, a persistent, automated haze of reflective materials still following its original programming long after its creators are gone. This concept, while still firmly in the realm of speculation, at least attempts to bridge the gap between the need for an intelligent cause and the observed fluid nature of the phenomenon. It acknowledges the mystery without ignoring the overwhelming physical constraints of the Venusian environment, leaving us with a haunting question mark hanging in the acidic air. Faced with an atmospheric phenomenon that defies conventional explanation, scientists have turned to their most powerful tool for understanding the universe, mathematics. They are constructing incredibly complex digital replicas of Venus's entire atmospheric system, attempting to simulate the mirror effect inside a computer to finally unravel its secrets. These aren't simple weather models, they are multi-layered, multi-physics simulations that attempt to stitch together the chaotic dance of fluid dynamics with the precise, probabilistic rules of quantum mechanics. The foundation of any atmospheric model is a set of equations known as the Navier-Stokes equations, which describe how fluids, including gases, move and behave. For a planet like Venus, applying these equations is a computational nightmare. Scientists must account for the insane super-rotation of the upper atmosphere, the violent turbulence created by hurricane-force winds, and the complex heating and cooling from both the scorching surface below and the intense solar radiation from above. They start by creating a three-dimensional grid that divides the entire atmosphere into billions of tiny virtual cubes. For each cube, the computer must calculate conditions like temperature, pressure, density, and wind velocity, and then figure out how each cube influences its neighbors every fraction of a second. The sheer scale of this calculation requires some of the most powerful supercomputers on Earth, running for weeks or even months to simulate just a few Venusian days. But the standard fluid dynamics models, as immense as they are, only get you so far. They can recreate the general chaos of the cloud decks, but they consistently fail to produce the sharp, coherent reflections we observe. The energy in these simulations always ends up being scattered and absorbed, never organized into a perfect mirror. This failure is what forced modelers to venture into far more exotic territory. They began integrating principles from quantum field theory, attempting to simulate how vast collections of particles might behave not as individual droplets, but as a unified quantum system. This involves writing entirely new sets of equations that describe the potential for macroscopic quantum states, like Bose-Einstein condensates, to form under extreme pressure and temperature. The models test whether trillions of sulfuric acid droplets could become entangled or synchronize their vibrations, creating a temporary, continent-sized quantum object that could reflect light as a single, cohesive surface. The most advanced models now merge these two worlds, the large-scale chaos of fluid dynamics and the minute precision of quantum mechanics, into a single, incredibly ambitious simulation. The results are fascinating and deeply puzzling. In certain very specific virtual scenarios, when the models introduce just the right mixture of trace metals like iron chloride and bismuth sulfide, and then subject them to precise energy fluxes, they can produce fleeting moments of order. The simulations show thin, transient layers where droplets align and particle vibrations synchronize, creating a brief, shimmering reflective patch. It's a digital glimpse of the mirror, and it proves that such an effect is theoretically possible within the known laws of physics. However, this is where the models hit their limits. These simulated mirrors are frustratingly fragile and fleeting. They appear for a few virtual minutes before the programmed turbulence of the atmosphere inevitably tears them apart. In the real world, however, the reflections observed by Venus Express and other missions are persistent and stable, sometimes lasting for days over the same geographical region. The digital mirrors are also far weaker than their real-world counterparts. They can't replicate the intense, coherent bounce of energy that our telescopes detect. The simulations can create a whisper of the effect, but not its full, powerful shout. This glaring discrepancy tells researchers that while they are on the right track, a crucial ingredient is still missing from their recipes. It could be an unknown chemical compound, a geological process pumping energy upward in an unaccounted-for way, or perhaps a deeper, more fundamental physical principle that we have not yet discovered and therefore cannot encode into any computer program. The mathematics isn't failing, it's shining a spotlight directly on the gap in our understanding, showing us exactly where we need to look next. To truly grasp the bizarre nature of the Venus mirror effect, we must zoom out and see it not as an isolated oddity, but as one particularly strange member of a family of planetary mysteries. Across our solar system, other worlds present their own atmospheric enigmas that defy easy explanation, and by comparing them, we can start to see patterns and possibilities. Take Jupiter, for instance. The gas giant's polar regions are home to auroras that are breathtakingly powerful and utterly perplexing. On Earth, our beautiful northern and southern lights are created by charged particles from the sun channeled by our planet's magnetic field. But Jupiter's auroras are different. They are permanent, raging storms of light that shine with an intensity that dwarfs our own, and they persist even when the solar wind is calm. Scientists realize these lights are powered not by the sun, but by Jupiter itself, specifically by material being flung from its volcanic moon Io, which gets caught in the planet's immensely powerful magnetic field and accelerated down into the polar atmosphere. This reveals a fundamental principle. A planet's atmosphere can be profoundly shaped and energized by its relationship with its moons and its own internal magnetic engine, a dynamic we are only beginning to understand. Then there's Saturn's moon Titan, a world shrouded in a thick, hazy atmosphere of nitrogen and methane that eerily resembles a primordial Earth. Titan has a complete methane cycle, with rain, rivers, lakes, and seas of liquid hydrocarbons. But it also holds a curious mystery, an unexpected and persistent layer of hydrogen gas missing from its atmosphere. Based on our models of atmospheric chemistry, sunlight should break down methane in Titan's upper atmosphere, a process that should produce a specific amount of hydrogen that then slowly drifts down to the surface. But when the Cassini probe measured it, that hydrogen was nowhere to be found. One compelling theory suggests it might be being consumed by microbial life in Titan's methane lakes, a literally breathtaking possibility. Another, perhaps more likely, explanation is that there is a previously unknown chemical process or catalyst at work on Titan's surface, perhaps involving minerals we haven't yet identified, that is scrubbing the hydrogen from the air. This shows us that even on a world we've visited with a probe, the complex dance of atmospheric chemistry can still hold huge, fundamental surprises, with processes operating that are completely outside our earthly experience. Even our seemingly well-understood neighbor, Mars, has its own atmospheric puzzles. The red planet occasionally experiences vast, planet-wide dust storms that can shroud its entire surface for months. But more curiously, NASA Curiosity rover has repeatedly detected sudden, unpredictable, and significant spikes of methane gas in the Martian air. On Earth, methane is a potent signature of biological activity, though it can also be produced geologically. The mystery is its transient nature. It appears and then vanishes, suggesting something is either producing it in bursts or there is an unknown chemical process in the Martian soil or atmosphere that is destroying it with incredible speed. This has led to fierce debate. Are we seeing the faint, intermittent breath of subsurface Martian microbes, or is it the product of a strange geological reaction between water, rock, and the planet's thin atmosphere that we have yet to replicate in a lab? Like the hydrogen loss on Titan, the Martian methane mystery underscores that planetary atmospheres are not static backdrops. They are dynamic chemical engines where hidden reactions can produce fleeting, tantalizing clues. So where does this leave Venus and its mirror? When we place it alongside these other mysteries, its uniqueness comes into sharp focus. Jupiter's auroras, for all their power, are ultimately explainable through the known physics of magnetic fields and charged particles, even if the scale is immense. Titan's missing hydrogen and Mars's methane burps are primarily chemical mysteries, puzzles of unknown reactions occurring on or below the surface. The Venus mirror effect, however, is in a category of its own. It is not primarily a magnetic or a chemical puzzle, it is an optical and quantum one. It's not about something being missing or added, but about energy behaving in a way that seems to violate the fundamental rules of how light interacts with matter. The common thread weaving through all these phenomena is the idea of hidden reservoirs and unrecognized pathways, whether it's Jupiter's moon providing a hidden source of particles, Titan's surface hiding a chemical sink, or Venus's atmosphere concealing a hidden process for organizing energy. What truly separates the Venusian mystery is its suggestion of spontaneous order emerging from chaos. The other anomalies involve things being consumed, released, or accelerated. The mirror effect implies something far more subtle and profound. The atmosphere might be temporarily structuring itself, creating a lens or a gateway through a process we haven't yet imagined. It challenges us to consider that the keys to understanding these distant worlds may not lie in simply applying Earth's physics on a larger scale, but in discovering entirely new principles that only reveal themselves under the most extreme and alien conditions. Each of these planetary puzzles is a piece of a much larger picture, forcing us to expand our definition of what an atmosphere is and what it can do. The next decade promises to be the most exciting chapter yet in this investigation, as a new armada of missions, armed with technology that would have seemed like science fiction to the pioneers of the Venera program, sets its sights on unlocking Venus's secrets. Leading this charge are two flagship missions with complementary goals, perfectly poised to attack the mystery from both above and below. NASA VERITAS orbiter, which stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy, is essentially a global reconnaissance machine. Its primary tool is a state-of-the-art synthetic aperture radar system, so advanced it will map the planet's surface topography at a resolution hundreds of times greater than the Magellan mission, effectively giving us a high-definition video game map of the entire world. But beyond creating stunning visuals, this powerful radar will be specifically tasked with re-examining those infamous anomalous bright spots with incredible precision, searching for any subtle correlation between the mirror-like reflections and specific mineral deposits, volcanic fissures, or other geological features that could be leaking energy or exotic gases into the atmosphere. While VERITAS scans from orbit, the Da Vinci mission will take the direct approach, embodying the spirit of those brave Soviet landers but with 21st century sophistication. Da Vinci, or Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging, is a descent probe. It's a rugged, spherical laboratory designed to survive the plunge through the very heart of the mystery. As it free falls through the critical 60-kilometer altitude zone, its suite of instruments will conduct the most detailed atmospheric biopsy ever attempted. A mass spectrometer will sniff the air, identifying every molecule it encounters with the goal of finally detecting those theorized metallic compounds like iron chloride or bismuth sulfide. A laser spectrometer will measure the abundance of noble gases, looking for isotopic ratios that could reveal ancient volcanic outgassing events that might have seeded the clouds. Most crucially, an instrument called a tunable laser spectrometer will be able to detect and measure concentrations of specific gases down to parts per billion, searching for the chemical fingerprints of unknown processes. But the innovation doesn't stop with these NASA missions. The European Space Agency is planning its own contribution with the EnVision orbiter, which will carry a complementary suite of spectrometers focused on analyzing the chemical composition of the atmosphere and surface at different wavelengths simultaneously. This will allow scientists to create a three-dimensional map of how certain gases and aerosols are distributed, watching in real time how the strange reflective patches form, move, and dissipate over days and weeks. Perhaps the most daring proposal comes from the private sector. Rocket Lab, the American aerospace company, has plans to send a small, low-cost probe to Venus as early as 2024. While its mission is primarily to search for signs of organic molecules in the clouds, its simple radio transmitter could provide invaluable data on how its signal is affected as it passes through the atmosphere, offering a cheap but effective way to probe the electrical and reflective properties of the cloud layers. The true game changers, however, may be the instruments currently confined to laboratory prototypes. Researchers are developing a new generation of quantum sensors designed to detect minuscule magnetic fields and incredibly subtle gravitational variations. Deployed on a future orbiter, such a sensor could potentially detect the fleeting, localized warping of space-time or the unique magnetic signatures that some theories predict would accompany a large-scale quantum coherent state in the atmosphere. Other teams are working on LiDAR systems that use entangled photons, a quantum radar of sorts. This technology could fire two perfectly linked photons into the atmosphere. If one is absorbed or scattered, its entangled partner would be instantly affected, providing an exquisitely sensitive measurement of the atmosphere's density and composition at a specific point, potentially allowing us to literally see the structure of the mirror itself. The collective goal of this international fleet is to move from simply observing the effect to actively testing the competing theories, gathering the definitive data that will either confirm a stunning new state of matter or reveal a breathtakingly complex natural phenomenon we never knew was possible. The mirror in the sky is waiting, and we are finally building the keys to unlock its secrets. Imagine if we could decode the precise physics behind this atmospheric mirror and learn to recreate it here on Earth. The technological revolution would be nothing short of profound, touching nearly every aspect of our lives. Let's start with energy. The mirror effect demonstrates an almost perfect reflection of specific wavelengths of light. If we could engineer materials that mimic this property, we could revolutionize solar power. Picture vast, lightweight sheets suspended in the upper atmosphere, acting as orbital mirrors that redirect and concentrate sunlight onto solar farms on the surface 24 hours a day, regardless of weather or the day-night cycle. We could achieve a constant, uninterrupted flow of solar energy, solving the intermittency problem that has long plagued renewable power. Furthermore, the potential for developing entirely new forms of energy storage becomes possible. If the effect involves some form of quantum coherence, it might show us how to trap and store light energy itself, holding photons in a kind of suspended animation within a coherent field and releasing them on demand, creating batteries made not of chemicals but of contained light. The implications for communication could be equally transformative. Our current global network relies on a fragile web of underground cables, cell towers, and satellites, all vulnerable to solar storms, physical damage, and congestion. The mirror effect suggests a method for transmitting information not through physical cables or radio waves, but through coherent, reflected energy channels in the atmosphere itself. We could develop a system that uses the upper atmosphere as a natural waveguide, bouncing perfectly coherent laser-like signals across the globe with virtually no loss of strength or clarity. This would enable instant, ultra-secure, high-bandwidth communication to any point on the planet without any ground-based infrastructure, a leap forward that would make our current internet look like the telegraph. This technology might even pave the way for deeper space communication, allowing us to send tightly focused data streams across the solar system with unprecedented precision. Perhaps the most critical application lies in the realm of climate engineering and atmospheric control. The greatest challenge facing our civilization is managing the delicate energy balance of our own planet. The Venus effect is a natural, albeit extreme, example of geoengineering in action. By understanding it, we might learn how to carefully and precisely manipulate Earth's albedo. We could design smart, reflective aerosols that could be deployed in the stratosphere to temporarily and reversibly increase the planet's reflectivity, creating a fine-tuned global thermostat to counter the worst effects of global warming. This wouldn't be a reckless gamble, it would be a calibrated application of a proven natural phenomenon, giving humanity a potential tool to safely manage global temperatures while we complete the transition to a zero-carbon economy. We could learn to gently steer weather patterns, mitigate the intensity of hurricanes by disrupting their heat engine, or even end droughts by encouraging precipitation in specific regions. The most speculative yet thrilling possibility revolves around transportation and the very nature of space and time. If the more radical theories hold water, if the effect involves minute warps in spacetime or macroscopic quantum entanglement, then the door opens to technologies that sound like pure fantasy. We might discover the principles for creating stable, energy-efficient gravitational field controllers, enabling inertia-free propulsion for spacecraft. Instead of burning massive amounts of fuel to break free of Earth's gravity, a vessel could use a localized coherence field to effectively reduce its mass, allowing it to ascend effortlessly. For interstellar travel, the ultimate dream, understanding how natural planetary conditions might create transient wrinkles in spacetime, could provide the foundational blueprints for building our own stable wormholes or warp drives, not as devices consuming the energy of a star, but as elegant applications of natural physics we simply hadn't noticed were operating right next door. The Venus mirror effect is more than a scientific curiosity. It is a potential treasure chest of knowledge, holding the keys to technologies that could elevate humanity to a truly planetary civilization and beyond. Now we turn to the most unconventional and frankly mind-bending realm of speculation surrounding the Venus mirror effect, a territory where hard science begins to blur with the metaphysical. This is the idea that the phenomenon might not just be a physical anomaly, but one that could potentially interact with or even influence consciousness itself. It's a concept that pushes the boundaries of what we consider possible, forcing us to consider whether the atmosphere of a planet could be more than a collection of gases. It could be an active participant in a form of perception we don't yet understand. To explore this, we must first look back at history and the curious, persistent link between Venus and human visionary experiences. For centuries, mystics, artists, and even some scientists have reported profound, often reality-altering visions during periods when Venus was prominently placed in the night sky. The famous early 20th century medium Helena Blavatsky spoke of receiving cosmic knowledge from Lords of Venus, while the brilliant inventor Nikola Tesla, a man deeply grounded in the physical world, famously claimed he received the concept for alternating current in a sudden, blinding vision he directly attributed to the planet. Throughout the 1960s and 70s, during the peak of the UFO phenomenon, a significant number of contactee reports specifically described encounters with benevolent, humanoid beings who claimed to hail from Venus. Mainstream science has always dismissed these accounts as fantasy, coincidence, or psychological projection onto a bright, familiar celestial object. But what if there was a sliver of a mechanism, a scientific straw for these unconventional ideas to grasp onto? This is where the mirror effect theory takes a radical turn. Some interdisciplinary researchers, often working at the crossroads of atmospheric physics and neurobiology, have proposed a wild hypothesis. They suggest that the highly reflective, coherent energy field in Venus's upper atmosphere might not just bounce back light and radio waves. It could, in theory, also act as a reflector or amplifier for other, more subtle forms of energy we don't yet have the instruments to measure. One speculative idea involves the planet's immense ionosphere, a charged layer of atmosphere that interacts directly with the solar wind. If the mirror effect is somehow modulating this ionospheric activity, it could be generating extremely low-frequency electromagnetic waves that travel across the void of space. These waves, sometimes called Schumann resonances, are known to occur naturally on Earth and have been shown in some studies to have a faint but measurable influence on human brainwave patterns, potentially affecting mood and states of consciousness. The theory goes that during specific planetary alignments, when the solar wind is just right, this modulated energy could wash over the Earth. For the vast majority of people, it would pass entirely unnoticed. But for a tiny fraction of individuals with uniquely sensitive or uniquely wired neural circuitry, the visionaries, the creatives, the migraine sufferers, or those in meditative or dream states, this energy might resonate within their brains. It could act as a catalyst, triggering unusual neural activity that manifests as vivid visions, lucid dreams, or a sudden, unbidden influx of complex ideas. The content of the vision, whether it's a beautiful being, a technological schematic, or a spiritual revelation, would still be generated entirely by the individual's own mind, culture, and subconscious. The Venusian energy wouldn't be sending a message. It would be, in effect, ringing a bell that only certain minds can hear, and each brain interprets the ring in its own way. In this model, Tesla didn't get a blueprint from Venusians. His brilliant, hyperactive brain may have been inadvertently tuned by a planetary-scale phenomenon, unlocking a solution that was already simmering in his subconscious. This is without a doubt the farthest fringe of the mirror effect hypothesis, and it is met with immense and justified skepticism from the vast majority of the scientific community. The distances involved are astronomical, and the energy required to have any measurable biological effect across tens of millions of miles is likely prohibitive. Critics rightly point out that it is infinitely more probable that these historical claims are purely psychological, the product of coincidence, confirmation bias, or the human brain's powerful tendency to find patterns and assign meaning, even where none exist. Yet, the reason this idea persists, even as a thought experiment, is because it touches on a deeper question that science is only beginning to grapple with: the profound and mysterious interconnection between consciousness and the cosmos. It challenges us to consider whether our perception of reality is a closed-loop system, or whether we might be subtly, imperceptibly open to influences from our environment on a scale we are only just beginning to imagine. Whether you find it compelling or utterly fanciful, it serves as a powerful reminder that the greatest mystery we are ultimately investigating might not be in the clouds of Venus, but within the human mind itself. Long before the first telescopes turned toward its brilliant light, Venus had already captivated humanity, not as a cloud-shrouded planet, but as a celestial mirror for our deepest hopes, fears, and spiritual yearnings. Ancient civilizations gazing at the morning and evening star had no knowledge of sulfuric acid or runaway greenhouse effects, yet they intuitively perceived its dual nature, a single object appearing in two different guises, and imbued it with a powerful, reflective symbolism that echoes the mirror effect we study today. The Maya, renowned for their sophisticated astronomy, meticulously tracked Venus and integrated its cycles into their sacred calendar, believing its appearances and disappearances were tied to the fates of kings and the outcomes of war. They saw it not just as a planet, but as a divine eye in the sky, a reflective surface that could portend both great fortune and terrible calamity, mirroring the dualistic nature of life itself. This perception of Venus as a cosmic mirror extended across the globe. In Mesopotamia, it was the goddess Ishtar, a figure of both love and war, beauty and terrifying power. The Romans, who gave the planet its modern name, worshipped Venus as the goddess of love and beauty, seeing its unparalleled brilliance in the night sky as a reflection of divine perfection. These ancient interpretations, though rooted in mythology, reveal a profound intuitive understanding. They recognized that this brightest of planets was special, a world that seemed to reflect something more than just sunlight. It reflected our own human complexities and contradictions back at us. This cultural legacy is a testament to the enduring power of the Venusian enigma, a mystery felt long before it was scientifically defined. The invention of the telescope promised to shatter these myths and replace them with cold, hard facts. When Galileo first observed Venus in the early 1600s, he saw its phases, proving it orbited the Sun and placing it firmly within the realm of physical worlds. Yet, instead of dispelling the mystery, this closer look only deepened it. For centuries after, the planet's impenetrable cloud cover frustrated astronomers, acting as a literal mirror that reflected our own ignorance. Early observers like Giovanni Cassini mapped faint, shifting markings on those clouds, sparking debates that now seem charmingly misguided. Some proposed the surface was a global ocean, others a swampy jungle world teeming with life. The most persistent theory, popularized by astronomers well into the 20th century, was that Venus was a wet tropical planet, a twin to Earth's Carboniferous period. This wasn't just wild speculation, it was a scientific hypothesis based on the best available data, which was the planet's reflectivity and its position in the Sun's habitable zone. The clouds, it was thought, were water vapor reflecting the light of a hidden world below. Venus became a mirror for our aspirations of finding another Earth, reflecting our own planet's past and our hopes for cosmic companionship. The rude awakening came with the dawn of the space age, and the cultural reflection shifted from one of hopeful kinship to one of ominous warning. The first data from Mariner 2 in 1962 revealed a scorching surface temperature, shattering the dream of a tropical paradise. Then, the Soviet Venera landers transmitted their brief, haunting glimpses of a hellish landscape under crushing pressure. In the public imagination, Venus was transformed almost overnight from a benevolent goddess into a cosmic cautionary tale, a mirror reflecting our own planet's potential future should we lose control of our atmosphere. This new vision of Venus as a victim of a runaway greenhouse effect powerfully influenced a generation of environmental activists and science fiction writers. It became a symbol of ecological hubris, a dead world showing us the horrifying end result of a biosphere pushed beyond its breaking point. Yet, even as this grim scientific consensus took hold, the planet's strangeness continued to inspire a more esoteric and speculative thread in our culture. The persistent, unexplained anomalies reported by early probes provided fertile ground for authors and filmmakers. The mirror effect, though not yet named, found its expression in stories of floating cities suspended in the temperate cloud layers, a concept popularized by authors like Carl Sagan and Arthur C. Clarke. In the 1970s and 80s, television shows like The Twilight Zone and Star Trek featured episodes centered on a mysterious, veiled Venus that hid dimensional portals or alien beings within its clouds. These narratives intuitively grasped the scientific mystery of a world that refused to be fully known, a place where reality seemed to be distorted. The planet once again became a cultural mirror, this time reflecting our growing fascination with the limits of human knowledge and the possibility of realities beyond our own. This interplay between scientific discovery and cultural storytelling creates a fascinating feedback loop. Our evolving technological understanding of Venus directly shapes the myths we tell about it, and those myths, in turn, influence the questions scientists ask and the public support for missions to find answers. The early, romantic visions of a jungle world motivated the first wave of space probes. The later, dystopian vision of a greenhouse apocalypse fueled scientific interest in comparative planetology and climate science. Now, as the mirror effect and other atmospheric anomalies suggest a Venus that is far more complex and physically bizarre than we ever imagined, our culture is once again adapting. Modern science fiction novels are increasingly populated with visions of Venus not as a dead world, but as a realm of exotic physics, quantum wonders, and hidden dimensions, a setting that feels less like classical science fiction and more like speculative realism. Our stories about Venus have always been a reflection of the current limits of our understanding, and as that understanding expands into the realms of quantum mechanics and unseen dimensions, so too does our cultural imagination, forever chasing the secrets of the shimmering mirror in the sky. Naturally, such a radical and data-defying hypothesis has not been met with universal acclaim. In fact, it has cleaved the scientific community studying Venus into two distinct and often passionately opposed camps. This isn't a quiet disagreement in the halls of academia. It's a vigorous, ongoing debate that plays out in journal articles, conference panels, and research proposals, with each side marshalling evidence to defend their view of reality. On one side stand the mainstream skeptics, the stalwarts of conventional physics. Their position is one of disciplined caution, arguing that extraordinary claims require not just extraordinary evidence, but the exhaustive elimination of all ordinary explanations. Leading this charge are planetary scientists from established institutions like NASA, a jet propulsion laboratory, and several major European space agencies. They argue that leaping to conclusions about quantum anomalies or temporal reflections is not only premature but fundamentally unscientific. Their primary counterargument is one of complexity. They posit that our models of Venus's atmosphere, while advanced, are still simplifications of an immensely complicated system. We are trying to simulate a global, multi-layered, chemically reactive fluid under extreme conditions, and it is far more likely that our computers are missing a key piece of atmospheric mechanics, a novel type of cloud-particle interaction, an unknown catalytic chemical reaction, or a fluid dynamic instability we haven't yet conceived of, than it is that the laws of quantum mechanics are behaving in an entirely new way on a planetary scale. This skeptical viewpoint was powerfully articulated at the recent Venus Science Priorities Workshop, a major gathering of the world's top experts. A prominent researcher from Caltech presented a detailed analysis arguing that the observed reflections could be explained by a transient phenomenon he dubbed supersaturated metallic fog. His complex model suggested that under specific temperature and pressure gradients, volatile metals like lead sulfide and bismuth chloride could momentarily condense into billions of perfectly spherical, nano-sized droplets of identical size. This uniform army of particles, however fleeting, could act as a collective mirror. While other scientists pointed out the immense difficulty of maintaining such uniformity in hurricane-force winds, the presentation underscored the skeptical camp's core belief. The answer lies in known physics, just pushed to a breathtaking level of complexity we haven't yet mastered. Arrayed against this view are the interdisciplinary pioneers, a smaller but growing coalition of atmospheric physicists, quantum information theorists, and even a few cosmologists. This group, which includes researchers from universities with strong programs in theoretical physics, argues that the obstinate failure of every conventional model to reproduce the mirror effect's intensity and coherence is itself the most important data point. They contend that continuing to propose increasingly convoluted atmospheric solutions is like using 19th century thermodynamics to explain a laser. You might get close, but you'll never grasp the fundamental quantum principle that makes it work. For them, the mirror effect is not a puzzle to be solved within the existing paradigm, but a signpost pointing toward a new one. This perspective has found a vocal platform in publications like the Journal of Planetary Science and Frontiers in Astronomy and Space Sciences, where papers with titles like Quantum Coherence as a Potential Factor in Planetary Atmospheric Dynamics have begun to appear. These are not fringe publications, they are peer-reviewed forums where radical ideas are stress-tested. The researchers behind these papers are not claiming to have proof, but rather a compelling case for investigation. They point to the cold spots detected by Venus Express in the reflective zones, asking why a region brilliantly reflecting energy isn't heating up dramatically. They highlight the precise polarization of the reflected light, which suggests a level of organization that turbulent gases seem incapable of achieving. Their argument is not that they have all the answers, but that the questions being raised are too profound to ignore simply because they make us uncomfortable. The debate has even catalyzed the formation of new, dedicated research groups aiming to bridge this divide. The Venus Consortium, an international collaboration between several universities and private research institutes, has made the mirror effect its primary focus. Within the consortium, teams are split. One wing is dedicated to building the most sophisticated atmospheric fluid dynamics model ever conceived, throwing immense computing power at the problem. Another wing is working from the other direction, developing first-principle quantum models to see if macroscopic coherence is even theoretically possible under Venusian conditions. The goal is to either find a conventional solution with unprecedented computing power or to definitively prove that such a solution is impossible, thereby forcing a monumental shift in how we view physics. This internal divide mirrors the larger scientific conversation, a healthy and necessary tension between the steadfast rigor of established science and the bold, paradigm-shifting curiosity that drives discovery forward. The future of our understanding doesn't lie with one side vanquishing the other, but in the relentless, collaborative friction between them. The brutal reality of exploring Venus is that it actively fights back against our attempts to understand it, placing immense technical barriers between our theories and the proof we desperately seek. Designing a probe to survive entry is an engineering nightmare. The spacecraft must endure a descent through an atmosphere that is essentially a corrosive, high-pressure fluid, with temperatures that can soften and warp the toughest alloys long before reaching the surface. Every instrument, every lens, every seam must be armored against a constant rain of sulfuric acid droplets, a challenge that renders most of our standard, off-the-shelf space technology utterly useless. We are essentially trying to build a deep-sea submarine that can also function as a high-altitude research plane, all while being bathed in acid, a set of contradictory requirements that pushes materials science to its absolute limit. Even if we succeed in getting a probe there, its operational window is heartbreakingly short. The Soviet Venera landers, our only successful touchdowns, transmitted data for mere minutes before being crushed and melted into silence. This creates a crippling data bottleneck. Imagine trying to understand the complex, ever-changing weather patterns of Earth if you could only ever drop a single, simple weather station into the middle of the Pacific Ocean and it would melt after 2 minutes. You might get a snapshot of the air pressure and temperature at that exact spot and moment, but you'd have no context for how it fits into the global system, no understanding of storms forming or seasons changing. Our current data on the mirror effect is a collection of these precious, fragmented snapshots separated by decades, making it nearly impossible to track the phenomenon over time or understand its triggers and life cycle. Remote sensing from orbit offers a broader view, but it comes with its own severe limitations. Orbiting spectrometers can analyze the chemical composition of the atmosphere by studying the light that passes through it, but they are like trying to identify the ingredients in a foggy soup by looking at how a flashlight beam changes color as it shines through. The thick, global cloud cover acts as a frustrating veil, blurring and scattering the signals we try to capture. We can detect that something strange is reflecting energy, but pinpointing the exact altitude, density, and physical structure of that reflective layer from hundreds of kilometers away is incredibly difficult. Our instruments are inferring the existence of the mirror from its shadow, leaving massive room for interpretation and competing theories. These practical obstacles have acted as a perfect brake on discovery, prolonging the mystery for generations. Each mission is so expensive and complex that decades can pass between opportunities to gather new data, slowing the scientific process to a crawl. A researcher might spend their entire career waiting for the next piece of the puzzle to arrive, their theories frozen in time for lack of evidence. This glacial pace is why the debate between conventional and exotic explanations has persisted for so long. Without a constant stream of new observations, both sides can comfortably exist, each arguing their case from the same limited, aging dataset. The breakthroughs that will finally provide definitive answers are now taking shape, hinging on a new generation of hardened technology and sustained observation. The key is moving from fleeting snapshots to a continuous monitoring campaign. This requires not just one-off landers, but a fleet of long-lived atmospheric platforms. Ideas on the drawing board include specially designed balloons or aerobots that could float within the temperate cloud layer for weeks or even months, acting as mobile weather stations drifting through the very heart of the mystery. These platforms, equipped with miniaturized laboratories using cutting-edge materials resistant to corrosion, could sample the air continuously, directly measuring the size and composition of particles in the reflective zones and hunting for those elusive metallic compounds or unusual chemical signatures. Complementing these atmospheric drones, we need orbiters equipped with next-generation active sensors. Instead of just passively reading the light that bounces off the clouds, future missions could use powerful LiDAR systems that fire precise laser pulses into the atmosphere, mapping the density and structure of the cloud layers in 3 dimensions with centimeter-scale accuracy. This would be like using sonar to map the ocean floor, allowing us to finally visualize the architecture of these reflective layers and see if they possess the smooth, coherent boundaries that a true mirror would require. By combining these two approaches, long-term in situ sampling and precise orbital mapping, we can transition from guessing about the mirror effect to directly observing it in action, gathering the continuous, high-resolution data needed to end the debate and write a new chapter in planetary science. Perhaps the most profound implication of the Venus mirror effect is how it has become a central talking point in one of the most ambitious debates in modern physics, the multiverse hypothesis. This isn't about science fiction portals to alien worlds, but about serious scientific proposals that our universe might be just one bubble in a vast cosmic foam of realities, and that Venus could be a place where the walls between these bubbles are unexpectedly thin. The planet's bizarre atmospheric behavior provides a rare, observable anomaly that physicists can use to test ideas that were once considered purely metaphysical. The core of this connection lies in the fundamental nature of the mirror effect itself. Its defiance of conventional physics suggests that our models of the universe are incomplete. One compelling explanation, pursued by a growing number of theoretical physicists, is that what we're seeing isn't a reflection within our own dimension, but a literal glimpse into another. In certain branches of string theory and quantum gravity, our 3-dimensional reality is viewed as a membrane or brain floating in a higher dimensional space. Other brains, other universes with their own physical laws, could be floating right alongside ours, separated by a minuscule distance in an unseen dimension. Under the right conditions, these brains could theoretically vibrate or ripple, briefly touching and influencing one another. This is where Venus enters the picture as a potential natural laboratory. The planet's upper atmosphere exists in a state of extreme thermodynamic and chemical stress, a cauldron of energy that some models suggest could be powerful enough to create microscopic wrinkles or resonances in the fabric of spacetime itself. These tiny imperfections might act as windows, allowing energy or information from a neighboring brain to briefly leak into our own. The inexplicably coherent reflections we detect could then be interpreted not as light bouncing off a cloud, but as light, or a form of energy we don't fully understand filtering through from a parallel reality where the physical properties of that atmospheric layer are slightly different. It would be a natural, planet-scale version of the experiments physicists hope to conduct with future particle colliders, searching for evidence of extra dimensions by looking for energy that seems to disappear from our universe, presumably having leaked into another. The mirror effect also provides a potential observational test for the controversial many worlds interpretation of quantum mechanics, which proposes that every quantum decision spawns a new, branching universe. A major criticism of this theory has always been its alleged untestability. If we can't interact with these other worlds, how can we prove they exist? The anomalous reflections on Venus offer a tantalizing possibility. If the atmosphere can achieve a large-scale quantum coherent state, as some researchers speculate, it might momentarily bridge the gap between these branching realities. The effect would not be a stable gateway, but a fleeting interference pattern like two radio stations briefly overlapping. The strange, structured nature of the reflections, their specific frequencies and polarizations, could carry the fingerprint of this quantum interference, providing the first ever empirical data to support a theory that has, until now, existed entirely in the realm of mathematics and philosophy. For cosmologists, Venus represents a unique case study in how multiverse dynamics might manifest on a planetary scale. In the inflationary multiverse model, our universe is one of many that bubbled up from a primordial quantum foam, each with its own unique set of physical constants. Most of these universes would be sterile, incapable of forming atoms or planets, but some, with constants finely tuned like our own, would allow for life. The problem is that these universes are forever separated by expanding voids of incomprehensible scale. However, if they originated close together in the inflationary field, they might remain tenuously connected by quantum threads or entangled patches of spacetime. A planet with an atmosphere as violently energetic as Venus's could act as a focal point for these residual connections, its atmosphere serving as a sensitive membrane that quivers with the influence of a nearby, almost identical universe. Studying the exact conditions under which the mirror effect appears and disappears could provide clues about the fundamental structure of the multiverse itself, turning a planet in our own solar system into the most important natural experiment for answering one of physics' ultimate questions. As we stand on the verge of potentially understanding and even replicating this extraordinary phenomenon, we are forced to confront a deeply philosophical and ethical dilemma. The very act of intense investigation, of sending probes and firing lasers into that atmospheric layer, could itself be an intervention. We are contemplating poking and prodding a system of immense complexity and power that we do not yet comprehend. The history of human interaction with natural systems is littered with examples of well-intentioned interventions that spiraled into catastrophe. The introduction of cane toads in Australia to control pests or the use of lead in gasoline for better engine performance are stark reminders that solving one problem without understanding the full web of consequences can create far greater ones. The parallel to our current climate crisis is particularly chilling. For over a century, we have been conducting a massive, uncontrolled experiment on Earth's atmosphere by pumping billions of tons of greenhouse gases into it. We did not set out to dangerously warm the planet. We were simply harnessing energy for progress, largely ignorant of the delicate balance we were disrupting. Now, as we consider intentionally altering another planet's atmosphere to study it, we must ask if we are about to repeat the same arrogant mistake. What if our probing disrupts the very conditions that maintain the mirror effect stability? Could we inadvertently trigger a cascade failure in Venus's already extreme climate, or worse, unleash a process that we cannot stop? This isn't just about potentially harming Venus. The speculation that the effect might involve quantum states or even connections to other dimensions raises stakes that are almost unimaginable. If the mirror is somehow a natural, stable gateway or a focal point for energies we can't measure, our attempts to analyze it could be like throwing a rock into a perfectly still, reflective pond. The ripples might not be contained to Venus. Theoretical physicists have long pondered the potential dangers of high-energy experiments, with some suggesting that creating certain quantum states or micro-black holes could have unforeseen consequences on a universal scale. While this sounds like the plot of a science fiction film, the underlying principle is a scientific caution. Do not experiment with forces you do not understand in systems you cannot control. Furthermore, there is a powerful argument from a perspective of cosmic preservation. If the Venus mirror effect is truly a unique and natural wonder, a one-of-a-kind phenomenon in our solar system, do we have the right to risk damaging it through our curiosity? We would be outraged if a corporation proposed strip mining the Grand Canyon for its mineral wealth, destroying its natural beauty for short-term gain. Should we not extend a similar ethic of preservation to an atmospheric phenomenon that may hold secrets about the fundamental nature of reality? Our first impulse is often to exploit, but perhaps our role as a budding interstellar species should be first to observe, to understand, and only then, with the utmost humility and caution, to carefully interact. This doesn't mean we should halt all exploration. The potential benefits for energy, communication, and our understanding of physics are too great to ignore. But it does argue for a new paradigm of planetary exploration, one governed by the precautionary principle. Our mission protocols need to be designed not just for maximum data return, but for minimal impact. We must develop and agree upon international treaties for atmospheric interaction, similar to the Outer Space Treaty that prohibits claiming celestial bodies, but focused on preserving environmental and dimensional integrity. The quest to unravel the mystery of the Venus mirror effect is perhaps one of the most exciting scientific endeavors of our time, but it must be pursued not with the reckless ambition of a conqueror, but with the respectful caution of a guest entering a sacred and astonishingly powerful cathedral of nature. So where does all of this leave us? We began with a simple, almost poetic question about a mirror in the sky, and we've journeyed through a labyrinth of competing ideas, from exotic metallic fogs and unknown chemical reactions to macroscopic quantum states and speculative dimensional windows. The evidence for the phenomenon itself is now undeniable and etched into the data from decades of missions. We have the persistent, anomalously bright radar reflections over specific highland regions, the intense and coherent infrared flashes detected by Venus Express, and the bizarre temperature inversions and clear zones reported by the brave Venera landers as they fell. This is not instrument error. It is a consistent signal, a real and measurable atmospheric behavior that stands in direct contradiction to our established models of physics and chemistry. Yet for every compelling piece of evidence, a dozen unanswered questions spring up in its place. What is the precise catalyst that initiates this incredible order within the chaos? Where does the immense energy required to sustain it truly originate? Is it a self-reinforcing atmospheric circuit we simply haven't learned to model, or could it point toward something far more profound? A new branch of physics that only manifests under such extreme planetary conditions. The sheer number of plausible yet unproven theories is itself a testament to the depth of the mystery. We are in the unique and thrilling position of having a dozen keys, any one of which might unlock the puzzle, but we lack the final, definitive data to know which lock they fit. This is the very essence of the scientific frontier. The Venus mirror effect represents that beautiful and humbling moment where our known physics ends and the great unknown begins. It is a glaring anomaly that has not yet been smoothed over by explanation, a raw nerve of curiosity that reminds us our understanding of the universe is still wonderfully incomplete. This phenomenon doesn't just challenge a few minor assumptions, it questions the very way energy and matter are supposed to interact in a dense, turbulent medium. It forces brilliant minds to consider possibilities that were once confined to theoretical papers and conference hallways, bringing them into the mainstream of planetary science. The investigation is far from over. In many ways, it is just beginning. The upcoming VERITAS, defy, and EnVision missions represent our best hope yet to move from speculation to solution. They are not just going to take more pictures, they are going to conduct a forensic investigation of an entire world. With every atmospheric sample taken and every new radar map generated, we will be testing these competing hypotheses, systematically eliminating possibilities and hopefully zeroing in on the truth. The greatest discovery these missions could make is not necessarily confirming one wild theory over another, but perhaps revealing a third, even more astonishing option we haven't even had the imagination to consider yet. This is the endless capacity of the universe to surprise and humble us, to remind us that no matter how much we learn, there will always be another layer of mystery waiting to be uncovered. The shimmering clouds of Venus, once seen as a simple barrier hiding a dead world, are now a canvas for our most profound questions about reality itself. So we want to hear from you. After this journey through the science and the speculation, what do you think explains the Venus mirror effect? Is it a strange yet natural atmospheric process, a glimpse of quantum physics on a grand scale, or something even more extraordinary? Share your thoughts in the comments below, and let's continue this incredible conversation as we watch together for the next great revelation from our mysterious